Okay, Richard, so we've got our work holding set up, but I can't help notice we're not quite at the stage of creating toolpaths yet. We've got a lot of some CNC machining tools ahead of us. So what are we going to talk about next?
Yeah, perfect. I'm not letting you loose on the machine just yet. What we really need to look at now is the tooling that we're going to choose. So on the front of the table here, I've sort of broken down a really common assembly that you might see. So starting with the tool tip itself, that's the end, that's doing the cutting, that's the business end of what we're talking about. We then go back and we've basically got everything now that's going to try and attach that piece of solid tungsten carbide into our machine. Now, different machines have different spindle noses. So the back end of the tooling now, or the tool holder, different people call them different things, does the job of connecting the solid piece of tungsten carbide to our spindle nose in our machine. Now, do you remember me harping on about standardization? The same thing with tool holders. So our machine here is a BT40 machine. You can get lots of different BT, you can BT 30, 50, 20s. One of the things here though is there's also HSK. So HSK is another standard. This is a HSK 100. You can get HSK 63. Don't get me wrong, you're probably going to have to mix and match eventually in your shop. But what I would say is when you look at a new machine, potentially think about having the same back end, having the same spindle nose. You've just invested in 100 tool holders for your BT40 machine. If you go and buy a machine that's HSK 63, well, guess what? You've got to invest in another set of tool holders. Nothing wrong with that, but it's definitely something to just make a decision on.
And when you talk about standardizing there on the tools, can I use a BT40 with a BT50? No,
they're
so
physically different size.
For the thing.
Yeah. So that's the back end. There's a bit in the middle. So this is basically where different manufacturers have different ways of gripping the tool. So it's about the tool itself, its connection to the machine, but how do we grip that tool? This is a very sort of universal way of having a sprung-loaded collet that's pushed inside of a taper. So as it gets pushed in that taper, it's going to close up and grip the tool. Now, the problem with this, it's very universal, very versatile, but it's a spring. And springs by nature will deflect. So that is one problem you can have with collets, is as you push the tool hard, it actually deflects the tool. So just something to bear in mind. I mean, for a lot of applications, something like this is perfectly fine, but maybe if you're going down to really heavy roughing operations, a collet might not be the right choice for you. You're going to have to just have a few different systems around you and choose what's best. So that's the holder portion. The tool itself. Now, lots of different tools. This is a end mill, a flat end mill. It's got flat sides, it's got a flat bottom, so it's really good for roughing operations and also creating straight cuts or flat cuts on a component. Extremely efficient at doing that. They come in all different shapes and sizes. This is a two cutting flutes. You can even get little 0.5 millimeter end mills. Size does matter. This is probably more useful to some people than a tool like this. You've just got to look at what you need to use. My advice is choose the biggest tool that's going to fit inside the feature you're trying to machine. The larger the tool, the more rigid it is, the harder you can hit that material.
Got it. And how do the flutes affect your ability to cut material?
Okay, very interesting. So a lot of the way the flute's designed is the difference between normally roughing and finishing. We normally say a finishing cutter has fewer flutes than a roughing cutter. The roughing cutter having more flutes gives it more rigidity. You've got more teeth to do the cutting, but that can also sacrifice surface finish. So I wish I had a one-stop answer for you that was the right tool to choose, but you're going to have to look at the feature on your part and then choose it. We've then also got ball nose tools. So this is where you've got a complete hemisphere over the top. We spoke about the end mill being for flat and straight finishes. This is where its 3D finishing comes into the matter. It's going to be where you're looking at profiling a 3D form, or maybe even just doing a little break edge chamfer on something.
And what about this tool here? So I can see there's some kind of like burnt marks along the tool holder. What's going on there?
Okay, interesting. This is a different system. We talked about the collets and the sprung-loaded nature of those. This is exactly the same as this, but just a different size. This is a shrink fit tool holder. So So here we've got a material that we're going to heat up. That's then going to expand. Now our tools are mainly tungsten carbide in this shop anyway. Tungsten carbide has a very low coefficient of thermal expansion, so the tungsten carbide is not going to expand. So we expand the holder, we drop the tungsten carbide in, and then we cool it to shrink it around our tool. That means we've got a very good grip. Can you spot what's different between this tool holder and that tool holder?
So, I mean, this looks like it's got less components on it. It looks like, I mean, it's noticeably much thinner than this one.
Okay, really good point. Exactly what I wanted you to pick up on. So, imagine you're doing a finishing process deep inside of a cavity. You've got to battle with this holder potentially hitting the sidewalls of your parts. Now, think about how slender this tool is. You can really get down much better access in deep cavities. So that's one reason why you might choose a shrink fit holder over a collet chuck. However, don't be the person that puts a HSS steel tool into a shrink fit holder. Because it expands the same as the holder, it's never coming out. Every apprentice has done it and they'll never live it down. So don't be that person.
Are there any other disadvantages to shrink fit versus a collet tool holder?
I mean, they cost a lot more to start with, so that might be prohibitive for your application. You need an induction heating machine to actually expand them. They can also not provide as much gripping force as some other tool holders. But again, what we said before, these can be really useful when you've got those finishing operations where you're not too concerned about pull-out force on our tool holder then.
Got it. And I noticed this tool here, there's a different color of the tool versus the kind of shaft of the tool. Is there something interesting going on there, perhaps?
Okay, that's the coating. So if we look at these two tools, they're both tungsten carbide, they're both the same base material. You can tell by the shanks are the same color. This has a different coating on it to this one. The coating is going to be dependent on the material you're cutting, how hard you're cutting it, is it finishing, is it roughing? Coatings can do a lot of different things. They can make the tool more tough. They can make it less susceptible to chipping. Again, I wish I could just give you that one-stop solution. When we're doing aluminium on our component, we're probably going to get away with no surface coating. It's a very soft material. We don't need a surface coating on our tool there.
Got it. So on that topic, we've had a look at all these different types of tools. Which ones are we going to need to machine our part?
Okay, we're going to need more than one tool to start with. So think of the geometry on our part, a big pocket. So we've got a big pocket we need to rough out. Not this end mill, but we're going to have a long end mill. Also, without getting too deep into the weeds, tools are normally rated in what we call times D, so times diameter. You've got a 10 mil tool that's 5 times D, so a 5 times D tool at 10 millimeters diameter is 50 millimeters. So that's something to bear in mind. So we're going to need to look at how deep is our pocket, and that's going to give us an indication then of the diameter tool we need. So we're going to be using a flat end mill for taking our pockets out. We've then got some holes on there. So we'll be using a drill to drill those holes, and they're also tapped. They're also threaded. So we'll be using a tap to thread those holes as we go then. And we also got some nice chamfers, which will be using a chamfer mill, which you could also class as like a form tool. There is a form on the end of it that's going to cut a specific shape.
Okay, so we've talked a bit about the tools we're going to use to machine our parts. What's the next stage? Okay,
perfect. We need to have a representation of these in Fusion. I've got a tool library of all the tools in my machine. I'm not going to give that to you. You're going to make your own library. The important thing is then it's yours. You can share it. Everyone in your shop can use it, and you can all have the correct tools in the library for your machine then. So there's a couple of different ways that you could approach this. Are your tools unassembled like this and you're going to load them into your machine, or are they already in your machine and you need to make the tool library? We're going to quickly look at both of those. So let's start with modeling up this tool holder and this end mill. Let's go into our tool library. And let's create a holder to start with. And now our description. So I would say the description I would normally put as the manufacturer's number on here. So that's BT40 SK16-120. And the vendor is Nikon. Right, let's go into our holder geometry. Let's add a new segment. Now our top segment here is going to be 25 millimeters. And the diameter is 63. Perfect. Now let's add a new segment for the bottom. That's 90 by 40. Now we could go and we could model every last little feature on here, all these chamfers, this ring, but we really just want the worst case scenario of what's possible on here. That's all we need for our holder at the moment, so hit accept.
Sounds good. And this is just going to be used to make sure that it's not going to collide. This is an extra check, essentially.
Yeah, definitely. So when you're looking at your toolpaths in Fusion, you can use this in your simulation to make sure you haven't got any places where your holder's going to gouge into the part. You could also think about using this in multi-axis operations for automatic collision avoidance.
Okay, cool. So we've got a holder added.
Yeah.
How about the tool?
Yeah, so let's create a flat end mill now. Okay. Description, this is going to be your choice. You know, I can't tell you what you should put as a description. I mean, if it was me, I'd call it a 60mm end mill, and I might even put alley afterwards, because this is specific geometry for aluminium. Yes, it might work on other materials, but it's an aluminium tool, really. Product ID, I can read a code on here. So that's 44900. Perfect. Okay, and then when we go to cutter, we've now got some different geometries. Let's work our way down. It's a flat end mill in millimeters, number of flutes. How many flutes can you see on here?
That looks like 3 to me.
Yep, correct, so it's 3 flutes. And its material is solid carbide. Right, diameter, 16 millimeters. Overall length of the tool is 125. Let's leave length below holder for the moment. Shoulder length, I haven't got a shoulder on here, it's a straight shank all the way down. So I will set that to my flute length. Okay. My flute length is 67, so that's right from the tip to where the last bit of the cutting portion is. So do 67 for the flute length and 67 for the shoulder length. Now, for my length below holder, shall I just put it in 2 millimeters and tighten it up so I've got the most sticking out? What do you think about that?
I mean, I'd put it a bit more in than that, to be completely honest with you.
Yeah,
that
exactly.
Bit,
So you want this to be in as far as you can to get the best grip on it and also the least leverage effects, while you're also then having the most reach you can on the tool. So I know our part is 75 millimeters deep. So from the top of it to the bottom of it is 75 millimeters.
Okay.
So if we put this in our hollis, and if I just put it to at the end of the flutes, how long are we? We're 77. So I'm going to actually set my calipers here to 80. And I'm going to put my stick out here as 80 millimeters.
Right.
So there we go. I'll tighten this up with our C-spanner later, but for the moment now, that's our tool. There's a few more things we need to do. If you go onto our holder tab, let's associate that holder now back with this tool. Perfect. Is that looking a bit more representative of what we got on the table now?
It looks pretty good. It looks pretty good. And I'm interested, you know, just how accurate do we have to be when we're putting in these kind of measurements?
Okay, so, I mean, your diameter needs to be accurate because that's going to define the way your toolpath is. The rest of it is more around collision detection. Yeah. So I'd say if you're measuring your length below the holder and it measures at 75.1, I'd maybe rank down to 75, always be a bit on the safer side. So if anyone was to adjust the tool, put a new tool in, you've always got that bit of extra wiggle room.
Got it.
Cool. Onto our cutting data tab now. So this is going to be the speeds and feeds that our tool should be sort of cutting at. Now, the manufacturer will be able to provide you recommendations for this, but they don't know the exact machine, spindle, work holding, part rigidity that you're doing, so they can't give you the most optimized speeds and feeds out the book. But what they can do is give you a good baseline. I know for this end mill, they'd recommend running it at about 10,000 RPM. So if you put that in there, that's a surface speed of about 500 meters a minute, and they recommend 0.1 feed per tooth. So if you know what the feed per tooth is, a 0.1. And that's sort of a baseline then that they suggest that you work from with this tool, for example. Okay. Now onto our post-processor tab. What tool is this in our machine? It's tool 1. Nice and easy. It's tool 1, it's offset number 1. That's really important in the machine, that the tool number and the offset number is correct in Fusion and what's on our machine then. So those two should always match.
Got it. And where does it get this offset from?
Okay, so in the machine we've got behind us, it's set up that the tool number is always the offset number. You can make it different, but that's its default way of happening. The offset number is collaborating with a table then that's inside the machine that's got the measurement from the spindle nose, which will be here, down to the tip of the tool.
Got it.
So that distance then is kept in the machine, so it knows when it calls this tool up, it knows where the spindle nose is, and then it knows where the tip of this individual tool is. Of course, all the tools are different lengths, and they're stored in a table then inside the machine.
And is that data that is coming from Fusion, or is that being set up on the machine?
That's been set up in the machine with our tool setter. Don't worry, you'll get some chance to actually program that later and get it on there.
Brilliant.
So perfect. I want to grab the next tool out of our machine, and then we can actually get that going. So I'm just going to call our tool up. Perfect. We've got our drill here. So our drill's going to be our next tool. Do you want to get that started on there to go? Thankfully, we've got the same holder as last time. Now, a bit different. Rather than measuring it and writing all the information out, I've actually got our book from our manufacturer with all the cutting details on. So I can see here, this is a 4.2mm drill, and I can see all of the lengths. So let's create this now. Description, 4.2mm drill. I mean, I would actually put on here M5 pilot in the description as well. Completely up to you, but that tells me that this is the pilot drill for an M5 tapped hole. The vendor is SGS. And the product ID on this tool is 65172. That's just going to help when you get to reordering this. You know exactly what it was and where to reorder it from. Perfect, it's a drill, it's got 2 flutes, it's solid carbide. Diameter is 4.2. Shaft is 6. Overall length is 74. Again, we'll check our length below holder in a second. Our flute length is 29. Our shoulder length is 36. And let's check our length below holder. So again, this is something that you need to manually measure. So again, 45.8 is our actual. I would go 45.5 in Fusion, just to give myself a little bit of room in case someone else puts this on and doesn't get it exactly right. Because the whole point of our Fusion tool library is we're going to share this with everyone in the shop. So no one has to keep redoing this process every day. We're going to have our shared tool library where we can all go from there. Let's choose our holder. Cutting data now. I can quickly look in our book here. Let me quickly find back that page we were on. So I've now found the cutting data in our book here. We've got aluminium alloys. Okay. So if we look at our spindles, people will look at surface speed to start with. So we've now found the page with our correct cutting data for our aluminium alloys, which we're machining for the tools we've got. It's suggesting here that we've got a surface speed of 75 meters a minute. And we've got a feed of 0.12 feed per revolution. So we now know the correct data from our manufacturer, and we can use that as a base point where we can go from there. Post-processor, this was tool 17 in our machine. Brilliant. So we've got our tools set up now in Fusion. Let's head onto the machine, actually set them up and set that length offset that we were talking about before.
Sounds great.
Thanks so much for watching. Don't forget to like, comment, subscribe, and click to watch the next video.